the cloud. So if you remember, we left off with the idea of coming up with volumes given a three-dimensional surface. And what we now need to do is we tackled it from the perspective where we're parallel to the YZ plane. Now we need to do it from the perspective where we're essentially tackling it from the parallel to the XZ plane. All right, so that's what we're going to do. First thing I'm going to do is establish what the XZ plane looks like along the lines of what I did with that with this guy here, you know, that plane, so that we can create the slicing, right? Or at least establish the slicing. So I'm going to try to keep my colors pretty consistent where possible. Here's X. Make that blue. Probably not the same shade, definitely not the same shade, but do what I can. All right, so that's my XZ plane, and I'm looking for a figure, or at least a plane that is parallel to that. So I'm going to just do a couple of copy paste jobs here. Let me actually get rid of this. All right, so that would be the XZ plane. And just to kind of make it a little bit more distinct, I'll use the green. Oh no, green represents Y. So let me stay away from that. I'll keep it as red. I didn't have to change the color. Let me go this way. So this is the plane in question, and what I want to do is take that plane and move it along the surface, creating slices. All right. So it's a little harder to see from this perspective, but it is doable. It's just a matter of, you know, just kind of suspending your disbelief. What I can do, and actually I probably, in all honesty, should have done this already. Oh, what did I do there? That's astonishing. What we could have done, or what I could have done, is change the orientation on Geogebra so that we can have a better look at it. So let me actually do that real quick. Get my Geogebra up here. I want my 3D calculator. Always a little iffy with the app, as you know. Get rid of the plane. Always get rid of the plane. So Z equals X squared sine. All right, so you can look for the function sine, or you can just start typing it in. If you could find the function, it makes life a little bit easier. Create the fraction pi y over 6, and so that's the function. But again, it's a little funky. All right, so you got the x-axis, the y-axis, and the z-axis. You know, you can kind of wiggle around this way if you want. You can hit the home button to have the standard orientation. The labeling, that's up to you. If you go to settings, turn on your x-axis label just for perspective. Y-axis, you really don't need the z-axis, especially if you're using the app. It's kind of a pain, but if you do it, that's fine too. All right. So then it's all labeled up there. You have X and Y. So now you have a little bit of a better look at what's going on here, all right, provided I typed it in correctly, right, which is always a bit of a challenge. Let me just make sure. Sine pi y over 6. All right, now what I did was when I created this graph initially, I restricted it to just the first quadrant, or well, really the first octant, right? So that's a little bit of a departure from what you see here, but you can kind of get an idea of what's going on. So if you kind of change your perspective to look along something along the lines like this, it makes it a little bit easier, right? But if I'm sorry, like this is what I meant to do. but I want planes that are parallel to the XZ axis. So when I'm looking at this, what I want to have is this perspective where I'm looking into the paper, but I want to take that and shift it over, right, as consistently as possible, right? So there's a way of handling that with GeoGebra that can be a little, it can be a little dicey, but yeah, you see, I've already paid the price for going with the app. You know, it's unfortunately what happens. So what I'll try to do is replicate this on my screen and then share my whole screen. That'll make life a little bit easier, I guess. You know, in an ideal world, in an ideal sense. Okay, so let me go to geogebra.org. I'll go to 3D, and I'll type all this stuff in again. And let me stop this share. And let me just make sure, actually, before I share, I'm going to minimize a whole lot of stuff here because there's, I got everything under the sun open on my screen here. Okay, so what I'll do is I'll just do it this way, and at least you'll get the view. That's the idea anyway. All right, so or at least my intended view. So again, it's Z equals, and there's nothing stopping you from doing this on your own, especially when it comes to a test or something like that. X squared. And like I was saying before, you just type in sine, it'll do it. Create the fraction bar first, pi y, oh, thinking of Desmos, pi y over 6. You get all that extra stuff that we really don't need. I'm not going to go through the process of putting the axes back on anyway. So we were looking at this orientation here, but if I want to create parallel slices, so slices parallel to the XZ plane, they would be in the form of y equals some constant, right? So y equals some constant that I'll call C. And it'll create the slider. So now I can slide back and forth and get a pretty decent look at what those cross sections ought to be like, right? Now, it's kind of hard to see, but anywhere where that light plane intersects the dark surface, I keep hitting the wrong thing. It creates a curve, right? And that curve is the cross section, right? But we're specifically only looking at the ones in the first octave, right? You could try an intersection, right? Because if you do an intersection, then it'll accept curve 1, curve 2 parameters. It'll accept function, object. So you could try an intersection between A and P is what they were called. See what comes up. Oh, I never finished typing the word. Yeah, sometimes it kicks it back because it is a multivariable function. It has a hard time with it. But if it worked, it would have been great. But this is what I'm getting at when I'm talking about those cross sections. All right, and you could also do it the other way because for the previous one, it was parallel to the YZ plane, right? So you might say if it's parallel to the YZ plane, it's in the form of x equals. So x equals also C, constant C. Turn this one off and leave the other one on. You can kind of revisit what we did in the first example. It gives you a nicer interactive view. So these are what those cross sections would look like, right? Just that intersection between the plane and the surface, right? So here it's somewhat parabolic, and in both cases it's somewhat parabolic, but it's really actually hyperbolic as it turns out, right? But I just figured I'd share that with you because visualization ends up being the hardest part of this whole thing, right? So I'm gonna go back to the iPad. I was worried there for a sec that it wasn't going to let me do it. So we're looking at, again, parallel to the YZ, the XZ plane. So we have to come up with a few different things. And if you use the first example as a model, or the first part of the example as a model, you can kind of get there. But you eventually want to get to the point where you can do these as standalone problems. Right? So just a quick recap, what we did was we found the area of a slice, right, which was the function itself dy. Right? So if I want the area of a slice, then I'm looking at the function itself times dx. Right? So let's see what that looks like. Or not. Oh, look at that. Okay, let's not look at that. Let's look at that. Okay, it actually came back, which I'm surprised by. It usually just crashes in that moment. Anytime I go back and forth with the sharing of screens, that's where we run into a problem, or I run into a problem. Let's be clear about that. Right. So we're looking at this cross section. So I'm going to get rid of that. So it's not a distraction. I'm going to bring it in. We're looking at, again, some sort of slice that's living along the x, parallel to the xz plane. And so it's going to have a thickness that's along the y-axis. Right? So just following the trend here, I'm looking at a curve that goes upward. Oh, brutal. It seems to go up infinitely, but I got to cap it off somewhere. So that's what I'm going to do. I'm just going to kind of cap it off based off of the function, the curve itself. It would have some sort of length associated with the available region, the bounded region in the XY plane. And because it is restricted, we know that it has a hard finish. So I'm just kind of roughing this out a little bit. Trying to give it a little bit of a three-dimensional perspective. So, and again, it's this surface, you know, it's the front end of it. It has no thickness to it, and we're just trying to simulate thickness to it. All right, now it's going to have some kind of cap. If we could ever get out to infinity, it would really kind of close in. So we're going to kind of assume the rest. You know, it's going to go something like this, and then kind of meet up. But that's not really as important as the idea that it's going to be a curve with some kind of thickness, and that thickness is going to be related to the y-axis. So that's my dy. Oh, that's supposed to be green. Now, in order to come up with the area itself, what I would need to do is kind of look at it from the other perspective. Right? So I'm going to look at it along the x-axis. So I'm looking directly on to the image, and I'm going to create an arbitrary rectangle. You don't need more than one. Right? That arbitrary rectangle is going to have a thickness associated with x. Right? And again, the trickiest part of this is the visualization, the visualizing. This is shooting on out to the x-axis. So I'll do that in dashed. All right, it's going to have a thickness along x. So the base of this rectangle is going to have a thickness in terms of x. The width of that rectangle, I'm sorry, the height of that rectangle is going to be associated with the function itself because it comes up and it intersects with that curve. That curve, regardless of where you are on the surface, is the f of xy curve, right? So the height of this rectangle is, I'll just write f for lack of space, but if I want the area of that rectangle, it looks kind of like on a good day, that looked like a parallelogram. I'm going to write rectangle. That's going to be equal to f times dx. Right? And again, it's f of x comma y. Right? So if we integrate that over the interval of 0 to 6, right? So starting here and ending here, integrate that, we get all of those rectangles, giving me the face of that figure. All right, so integrate over the interval and we get the area of all possible rectangles added together over that interval, which gives me the area of the cross section. And I'll say the face of the cross section. All right, and so if you take every one of those slices along the y-axis, find the corresponding area. So start here, work your way to, actually, I'm sorry, start at 0 and then work your way over towards 6. If you get every one of those areas, then what you would end up with is the volume. And I apologize, I boxed the wrong thing. Resize. That doesn't include the integral. All right. Not quite. All right, a little bit better. So that is the area of the face of the cross section. If I integrate all of those those areas, then over the interval, I will get the volume. All right, and so, oh, what did I write? Oh, I'm sorry. I started second guessing myself and I screwed the whole thing up. Yeah, no, that was fine. I boxed the right thing. I got to trust my instincts every now and then, right? Because I usually screw that up. That's why, right? So then this is going to give me all of those faces added together. All right. So this is going to give me I'll just write the volume of all slices added together. All right, and that's because the integral itself multiplied by dy gives you the volume of the slice, right? So it's kind of hard, I'm highlighting everything. It's like I'm highlighting nothing, but going from that innermost integral dx, if we take that and multiply it by dy, that gives you the volume of a single slice. If I integrate all those slices together over the interval of 0 to 6, then I get all the volume of all the slices combined, right? So either way, we should end up with the same integral. I'm sorry, the same result from integration. So we're looking at, and I'll do it in green, 0 to 6, 0 to 6 again, and then our function, but with the boundaries of no, I'm sorry, not the boundaries, the variables of integration, the order of integration reversed. All right, now these two things, because we're talking about the same solid, should amount to the same result. All right, so it becomes a question of, all right, well, which way do you want to do it? Because you do have a choice in the matter in most cases. I can't think of a situation where I'm going to tell you, all right, you got to do it this way, because I want, part of the fun is you going through the process and saying, well, I would never do it that way, because that way is going to take too much time and energy. All right, so you look at it from the perspective of the leftmost integral, you'd have to integrate that trig function. Not a big deal because it's not like a crazy trig function raised to a power. It's not a composite function with another trig function or another crazy function. But in the case of the left multiple integral, the innermost integration is a whole lot easier. So that's where we would spend our energy. Right? So I'd be looking at this as being 1/3 x cubed sine pi y over 6 over the interval of 0 to 6 popping in the 6 makes it simplify pretty significantly. I got all these different calculators here. I want to open a good one. So if I pop in the 6, I'm looking at 216 divided by 3. Was that 72? But I'm just going to double check that because I start second guessing myself. Once I make one mistake, you've seen it. Once I make one mistake, it all spirals out of control. Yeah, 72. So 72 sine pi y over 6. Now that's also integrated, but this time with respect to y over the interval of 0 to 6. All right. So single variable integral, a whole lot easier to handle because now I have different pathways to work this. Right. If you want to work it using the calculator, then that's perfectly fine. The one thing that I learned last time after staring at it for a couple times, and one of you helped me out, and I appreciate that, the parentheses. When you're putting an integral into Desmos, you want to make sure you have the parentheses there, right, to indicate what the integrand is. All right, so you do pi y, pi x, pi y, doesn't matter, as long as your dx or dy is corresponding with that choice. All right, so load them up twice, and then we want to get in a dy. And we get this number. And again, exact answers or inexact answer. There's a time and a place for that. It's really not this topic because the big challenge in this topic as we go forward is not, I've explained this before, it's not so much coming up with the integral, the result of the integration. It's more so developing what sort of integrand should be incorporated into your multiple integrals, right? And then what the order of integration ought to be. You know, that's the important stuff. So about 275 is fine. Yeah, and this is cubic units because it is a volume. Now, if you come across a multiple choice question that asks you to come up with the result and it gives you an answer that's in terms of pi or something like that, do it any way you want, and then just see which one is equivalent, which of the choices is equivalent to your decimal answer. So that part should be okay. Right. So you got Fubini's theorem, which tells us the order of integration is interchangeable. We know that because it says it right there, but more so, it has to do with what we just computed in the previous example. I didn't show you the result of the integration for the left version. Yeah, so you kind of have to take my word for it or do it on your own, but you'll see. You can check the previously completed notes too if you want, but ultimately they end up being the same. And so when that happens, it tells you that, okay, the order of integration didn't really matter. But it only doesn't matter because you're talking about rectangular bounds. All right, so the base area, so the area in the XY plane is rectangular in nature. All right? If it's anything other than rectangular, you got some other work ahead of you. All right. I got a little inconsistency with the type font here. So in number 2, where it says z equals x squared plus y squared, I'll take that as a typo if somebody wants to submit it. I got to change that in my notes. I got to clean that up. But we're looking at z equals x squared plus y squared. And we got the nice looking solid here. It's no big deal. But it's telling us, all right, well, we got a choice. I can integrate with respect to y first, then with respect to x, or I could do it vice versa. All right, so let's see what the story is. We would be finding the multiple integral of my f of x comma y, which is x squared plus y squared. All right, and that's going to be with respect to x or with respect to y. So I'm going to choose to do it with respect to x first. All right, the bounds are, this is a square set of bounds. All right, -1 to 1 on the x's and -1 to 1 on the y's. as integration problems go, multiple integration problems go, this really couldn't be any easier. That's not true. There's a lot of ways it could be easier, but this is a pretty easy one because integrating with respect to x gives us a 1/3 x cubed. With respect to x for the y squared is treated as constant, so this becomes plus x y squared. All right, so we're hanging on to the y squared, and then we're popping in, or we're popping a coefficient of x in there. All right, we'd have to do a little bit of crunching here because you look at it and say, well, I got an integral that's in terms of x and y. This is going to be crazy. No, because I'm going to plug in a -1 here. I'm sorry, -1 and a 1, and that's going to clean things up nicely. All right, so 1/3 x cubed with the x being a 1, so just 1/3, plus xy squared, again with the x being a 1 gives us a y squared, minus, or equality minus, 1/3 -1 squared, cubed, sorry, I think it said squared before too, and then cubed. -1 cubed is -1, so minus a 1/3. And again, popping in a -1, I get minus y squared. Unfortunately, this isn't a clean cancellation, but it's still going to clean up, right? So we're looking at 2 negatives make a positive, so meh, meh, meh. Combine our likes. We're going to look at 2/3 plus 2y squared integrated over the interval of -1 to 1 dy. All right. And again, do it any way you want. This one's not too bad to do by hand, but if you have a choice in the matter, I say that that choice should be that you let Desmos do it for you. But we're all, we all have our preferences. If you notice something like origin symmetry, where, for example, you have equal parts on the left side, on the right side, part of it's positive, part of it's negative, and it would cancel out and save yourself some time and energy, you can go for that. But that's not the case here because this is an even function. So the best you could do is find like 0 to 1 and then double it. But you know, that's kind of a waste of effort here. All right, so dy. And we get, okay, so this one will clean up to a nice fraction, so we might as well take it when we can get it. So 8/3. All right, now, since this one is substantially easier, or markedly easier, or just easier than the previous example, what I'll do is I'll actually tackle this the other way also. All right, so I'm just going to swap the bounds of integration. We're not looking at anything too different in terms of computation because we would still get the 1/3 something squared, but that's going to be associated with the y rather than the x. All right, so we're looking at x squared y plus 1/3 y cubed over the interval of -1 to 1. If I plug in a 1 for y, I'm looking at x squared plus 1/3 minus, and again, plugging in a -1, I'm looking at -x squared minus 1/3, and you can see that it's giving us the same thing, right? It's leading to the same result. So that cleans up to 2x squared plus 2/3 integrated over -1 to 1. This time dx is it's the same integrand over the same interval. So it's still going to be 8/3. Right? So not too difficult to demonstrate Fubini's theorem here. The one thing that we haven't demonstrated is that order is not interchangeable if the base region is, I'm sorry, it's interchangeable. It's just not, it's not interchangeable as easily as just swapping dx and dy, right? There's a methodology behind it that we'd have to get into, and we will. but Fubini's theorem, it works beautifully when you're dealing with a rectangular base area. Right? So now we just have to expand beyond that. Right? But we'll get there. We just have to take our time. I got a little proof here for you. Prove the volume of a cube formula is V equals S cubed in R3. So, you know, it's implied, and it's not stated directly, but it's implied that we would be dealing with this using multiple integrals. Right? So what I would first do is, you know, probably just draw a cube. So let me get, you know, just a nice visual going on here. So let me just draw a cube. We're going out, let's say 1 unit, but I'm not going to call it 1. I'm going to call it S. Okay, so S units in each direction. Now we know that length times width times height gives us the volume, and S times S times S would be S cubed, but that's not, it's not a proof, you know, not in the sense that we haven't used multiple integrals here. Right? So what I'm going to do is copy paste, get a nice looking sketch here. Hopefully nice looking. That's the ultimate purpose behind all this. Copy paste. And copy paste. Okay, so going up S units, you know, easier said than done, but we'll get there. Making a, hopefully, a representative looking figure here. Yeah, a little out of whack, but you can, you know what? This one, I don't even know why I bothered doing it that way. I can just connect them the old fashioned way. A little off, but you can live with it. All right. A little out of whack. Ugh, it's so bothersome. Yeah, I'm just going to deal with it. I pretend it's a perfect drawing instead of, you know, what I just did. And that's only, it only is out of whack because I eyeballed the horizontal and vertical axis, the plotting of the points. So it's definitely a little weird. But this plane that got highlighted, you know, and actually it's the happy unintended consequence, but that's Z equals S. Right? The bounds along the horizontal axes, right? So anything along the XY plane, this is S units away, right? So this is location S. So I'm really labeling, I'm leaning into this label of S, but what I can do is I can get these out of here so it's not too crazy, right? So Z equals S, and it's going from 0 to S along the x-axis and also along the y-axis, and it's a square basic region, right? So that's good news. I'm going to just kind of trim this down a little bit, make it look a little nicer. But, you know, quality of the drawing aside, it's pretty clear that that's at least attempting to be a cube. So what I would look to do here is find the multiple integral of f of x comma y, right? So my z function, dx dy or dy dx, it doesn't matter which way I go, all right? And that would be over the interval of 0 to s in terms of x and 0 to s in terms of y. And the only caveat here is that z itself is equal to s. All right, so I'd have to tackle the antiderivative of s with respect to x, well, s is treated as constant, right, in this context. So I'm going to focus on this piece here. The antiderivative of s with respect to x is sx over the interval of 0 to s. So what that gives me is s squared. And that actually right there, if we stopped right there, would be a nice derivation for the area of a square, right, in 3D or otherwise. All right. So because what this is doing is it's taking values under, and it's kind of hard to visualize, but it's taking values under the z function with respect to, you know, multiplied by the thickness along the x-axis. So if I go back to this original diagram here, and this is the thing people very easily lose sight of. We have an arbitrary rectangle that exists within that interval of 0 to s. And that arbitrary rectangle has, you know, if you're thinking in terms of Riemann sums, it has a thickness dx. If you take that thickness dx and multiply it by the height, which is z equals s, then you get the area of just a single one of those rectangles. Integrate it over the interval of 0 to s, and now you have the area of that entire side of the box, right, which is a square. Right? So we just derived the area of a square formula, but that's something you can do in 2 dimensions anyway. Right? So I'm going to integrate this over the interval of 0 to s, for quality s, dy. S squared is treated as constant, so the antiderivative of s squared is s squared y, going from 0 to s, which is going to give you s cubed, and that would be the volume of the cube. All right. So a lot of kind of moving parts here, but it gives you a little bit of a recipe for being able to handle the volume of any figure, because what we did is we established that, okay, for something that's well known, we know that the volume of a cube is s squared. It ought to be s squared. So when I'm looking for the volume of an ellipsoid, I'll be able to kind of replicate, you know, this approach just using ellipses rather than squares, right? But you get a lot of what you need out of this, right? And all this is doing when you integrate with respect to y is we're taking each one of these squares, right? So if I can kind of emphasize it a little bit, what I'll do is I'll grab the color that stands out. So this figure here, for example, which is the opposite side, if I take that and, you know, it's hard to see, but if I work my way through the entire open space, if you will, then, you know, because what we figured out by getting s squared was the area of this side. So then integrating it will give me this side, each one of these volumes added together. So this one, 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 blah, 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 all the way until we cover up the entire region, at which point we will have accounted for all the volumes. Right? And so in the end, the sum of all those volumes would give us the volume of the cube itself. Right? So it's a lot of theoretical stuff going into it, but it's pretty straightforward when you really think about it. All right. So then it brings us to the idea, well, what if the region in the XY plane is not a rectangle? You run into a little bit of an issue there. And by a little, I mean a lot, because it's not a simple matter of just saying, let me just swap the bounds of integration. No, I keep saying bounds of integration, the order of integration. All right. So we gotta be mindful of that. Right? And so there's a lot of textbook jargon here that talks about properties and things of that nature, but this is all kind of FYI stuff. I'm going to take you through the process in a particular sense, so that you get a good handle on it. Right. So we're revisiting this example except instead of having a rectangular base, a square base, we're going to have a non-rectangular base. In this case, parabolic, the intersection of two parabolas. Right. So what we have to do here is figure out what the bounds of integration, the boundaries of integration. I keep saying that. Jesus. Well, yeah, boundaries of integration definitely, but order of integration followed by boundaries of integration. And it's very hard to get when you say something very frequently and you say something else that's not quite as frequent. Kind of hard to get one phrase out of your mind. But anyway, we know it's going to involve the function z, or f of x comma y in some capacity. Just a question of, all right, well, how do I get the order of integration out of this? All right, so we look at the picture. It's symmetrical, so how I label it really doesn't matter in terms of the axes, but I'm going to call this one x and this one y because it's really what I intended, even though the color scheme may not be. No, I think this is actually the color scheme. So if I look at this as if it were the xy axis, I'm just looking at the cross section, what I'd be dealing with, and I'll just do it on Desmos here, y equals 1 minus x squared. That's one parabola. And y equals x squared minus 1. All right. The intersection of those two functions is going to establish the outermost bounds. All right. So now you can create a restriction on this. It's going from -1 to 1. All right. So you can create a restriction on this, but they're basically telling us that one way to handle this idea is instead of saying that I'm going to take my integral and just kind of take a shot in the dark and say, oh, well, I think it's going from this to that, this to that. Let's do y first, then x. No, you know what? I'm feeling like doing x first, then y. No, we don't do it that way. What we do is we work inside out, and I'll highlight here. We have our function x squared plus y squared. Okay. What we want to do is establish, based off of the nature of the functions in 2 dimensions, and I'm talking about the functions that represent the base area, we want to establish a variable expression that will give us the distance from the lowest point on the curve to the highest point on the curve. Lowest point on one curve, not even lowest, just a point on the bottom curve to the point on the top curve. Right. So I'm going to bring this in just so I can mark it up. Yeah, base. All right, so that's that base region. And just like in Calc 1, Calc 2, if I wanted to find the area between two curves, I'd be looking to find the distance between those two curves. So we create these the arbitrary rectangles. You know, if you remember that. Keep referring to them over and over again, but that's no guarantee people have any idea what the flip I'm talking about. The hope is that you do, though. All right, so here's an arbitrary rectangle. All right, that has a value of y. But specifically, y equals 1 minus x squared. Yeah. Now this one, also an arbitrary rectangle. Oh, holy moly. The molies are getting holy here. Okay, pretend that's not crap. Anyway, y equals x squared minus 1. All right. So that would be our two functions. Now, what I want is the total distance between the two. So as you know, if you want the distance between 2 points, you just subtract them, right? So I'll just make a little note of it here. I'm gonna go, you know what, I'll go light blue for those keeping score at home. This distance is going to be 1 minus x squared minus x squared minus 1. Now, you can clean it up if you want. You know, it's going to be just a 2 minus x squared. That's what you would do if you wanted to find the area of the base region. But the problem is, if you find the area of the base region and then extrude that into a prism, like you would, yeah, I think it was the first tech assignment, that's going to give you a solid in the shape of that base region. So that's fine, but it's not going to quite get the job done, right? Well, we just want in this case, so that's kind of the Calc 1, Calc 2 approach. All right, what we want is just an expression that represents the lower bound, so x squared minus 1, and an expression that represents the upper bound, 1 minus x squared. All right. Now, these are both y equations, or, well, they will be once I put a y equals in there. All right. So this is y equals y equals y. So it really is just a question of, all right, so what am I integrating with respect to when I go to figure out something like this? All right. So it's y equals 1 minus x squared on the high bound, x squared minus 1 on the low bound. For the substitution, that's the key ingredient here. And also, as I'm doing this, I noticed a little typo here. There should be these minus signs should be of the same quality. So I'll take that as a typo for bonus if somebody is in need of that sort of thing. All right. So anyway, when I integrate, again, it's just the idea of saying, all right, well, which variable makes the most sense here? Does it make sense to integrate with respect to x or integrate with respect to y? All right. So if I hope to substitute an x into my expression, then what I would be substituting that in for is the y, which is why I wrote the y here. All right. So this would be a dy. And so we can carry out this process. You know, we'll worry about the other integral in a second. But if I integrate this, we did it before, it's going to be x squared y plus 1/3 y cubed. See how we would be integrating that over the interval of x squared minus 1 to 1 minus x squared. It's kind of a matter of having the ability to substitute in for one function as opposed to the other. You know, so if I did this with respect to x, yeah, I'd have y's available, but it wouldn't be the same kind of quality of y. I'll get into what this looks like algebraically in a second, graphically in a second. Yeah, question.
On the example 4, all the way on the bottom, isn't that supposed to be 2 minus 2x squared?
2 minus 2x squared. Oh, no, I was just giving, when I did that diagram, oh, I see what you're saying. Okay, yeah, that's just a simple calculation error. Yeah.
Huh.
Thank you.
Okay.
So we can crunch these numbers. So when I pop it in, I'm going to pop in for the y here and here. So we're looking at x squared times 1 minus x squared plus 1/3 times 1 minus x squared cubed. And then minus basically same stuff again, this with x squared minus 1s. Okay. And so we can clean this up and see where it gets us. Yeah, and kind of getting us somewhere ugly in a hurry. But when I say clean it up, I don't mean go nuts and distributing the whole thing out, because that's just going to make your life a little bit more challenging than it needs to be. What I recommend is just clean it up, as in I have, use whatever algebraic skills you have in your toolbox, your tool chest, whatever. These are opposites of one another. Really, to cut to the chase, I'm saying, why not just factor out a -1 here so that we can make this negative x squared times x squared minus 1. Now for the light blue one there, I'd have to pull it out 3 times, but that's not a big deal. Because if you pull out a -1, a factor of -1 3 times, it's still going to be a -1. So minus 1/3 x squared minus 1 cubed. And then we can distribute through. We'll have negative x squared minus 1 minus 1/3 x squared minus 1 cubed, right? Which allows us to streamline this significantly. So we'd be looking at -2 x squared minus 1 minus 2/3 x squared minus 1 cubed. Right. Again, as always, barring any significant horrific algebraic issues. Right. So what we just figured out was the result of that integral, which is great. Now we just need to know, okay, now what? Well, in terms of x, this thing is going from, just based on what I see here in Desmos, this thing is going from -1 to 1. And so we're getting it from the other perspective here. And visually, like I said, visually this is kind of a bear, but I'll pull it up on Geogebra in a minute. Actually, I'll start typing it up now so that it can be kind of seamless when I do that. But it's just a matter of integrating this with respect to x, and that's going to be over the interval of -1 to 1 dx. All right. Now, if you want to factor out a GCF and try to clean it up further, that's your business. I would probably shy away from that, only because it's not going to clean it up to the point where I'm going to avoid any kind of meaningful work. So I hesitate to call something a waste of time or a waste of effort, but this is as close to that as you can get. All right. So -2 x squared minus 1, close it up, minus 2/3 x squared minus 1 cubed, and dx. And so we get about 1.143. Right, so cubic units. And don't be shocked or alarmed if you get some small number, because that happens pretty frequently. Really, in the end of the day, at the end of the day, you shouldn't be surprised when that happens, because if you think about the units, you could have something like a half a foot by a half a foot. That's a quarter of a square foot. But then when you get to the volume, that's 1/8 of a cubic foot. Right. Now you might say, well, 1/8 is kind of the classic misconception. 1/8, yeah, that number is smaller than 1/4, but 1/8 of a cubic unit is more material, more tangible material than 1/4 of a square unit. Right? So yeah, I mean, just go with something simple. Like there's no way mathematically, or at least in a physical sense, 1 square mile and 1 cubic mile could possibly be the same thing, even though they both have the same number. Right? So that's really all I'm getting at there. I'm just gonna put the final or finishing touches on this display, and then I'll switch over so you can see what I'm seeing. And we'll look at it from the perspective of the XY axis. All right. And I'll also get the curves in there. So let me stop that share, and I'll start this share. Here, share everywhere. I share. All right. So the issue is that when you want to come up with a curve in an XY plane, you run into the issue that you have to do it in a parametric sense, right? So one way I can handle that is to, because I don't want to type in y = 1 minus x squared, because it's going to give it infinite height. I mean, you could do that actually. You try it anyway, y = 1 minus x squared. I mean, there is value in doing that, but you can see it gets kind of messy pretty quickly. But if you're looking at this as just, a projection where you'd have the intersection between the two functions, then you can kind of get a sense of what the volume is that's being contained. It's hard to see, but really, and I'll get the y = x squared minus 1. Oh, that was weird. All right, I'll turn this one off. If you're looking at this projection here, right up on into the z axis, you can see that contained within this curve and this solid is some open space. That open space is the volume that we're looking for. Right? If I put this one in there, you can see, especially with top-down view, that there would be an intersection between the two functions. I bring it out a little bit. And that intersection, that intersection there, from here to, I can turn this one off. It's not letting me. Right, but from that paraboloid to its opposite paraboloid, there's that little cutoff beneath the curve, or within the curve itself. There is that region that contains some volume. Right, so it doesn't do a heck of a job of showing it, but you might be able to get a sense. Right, the better way of doing it is to use the curve function. Right, so we just have to do it parametrically. So I'd say t comma 1 minus t squared zero, because I don't want it to be anywhere on the z axis. Right, comma t comma 0. I'll say -10 to 10. All right, so you get that, and then I'll clean that up in a second. But then you could do the same thing, and I'll just duplicate it, because this is just t squared minus 1, and you get the opposition here. Now the intersection goes from -1 to -1 to 1. So if I want to change my t bounds, and it kind of gets a little messy when it comes to GeoGebra, but I can go from -1 to 1. That's easy enough. All right, it trims it. And so that's what we're looking at. Now, if I shoot that upward, I'd be looking at the area between this parametric curve and the surface. I'm sorry, the volume. All right. If you want a top-down view, you can kind of get a sense of what we're looking at. All right. So that corresponds with what I did on Desmos. It just doesn't look quite as nice, but that's really the idea. All right. The cross-sectional part of it is a lot trickier, because how do you get a visual on that? All right. The only way to really do that is to work with your your XY plane, I'm sorry, your XZ plane and your YZ planes and get those cross sections, right? So let me go back to the iPad. Assuming it wants to work, because I'm asking it to do a lot right now. So what you would be doing, again, just like we did before in the last set of problems, I'll use orange here to make it stand out. If I want to find intersections, or I'm sorry, cross sections where I'm integrating with respect to y, that means that the thickness would be along the y axis, right? Which means that I'd be looking at the XZ plane, right? So this would be the plane that I have in mind. Oof, ugly. No alibi. Try to make it look some. Well, I can live with that. All right. So it would be propagating this plane through the region here that would allow you to come up with your integral, right? So what would that look like? You know, you kind of do this just to get an idea, but I would be saying, all right, well, I got this part of the surface, let's say this guy up here, that's coming down somewhere, but I'll give it a little bit more height. Looks like it's intersecting over here. I'd be looking for this area, right? Now this figure itself would have a thickness, ooh, poor quality, looks devastatingly ugly, along dy. Right, and that's what we did there. And I would just kind of work my way back and forth. Now there is a corresponding part of the curve on the other side for symmetry, but that's the same idea anyway, right? And so the height of that function is z, and it's just a question of, okay, well, where is it starting and where is it ending? So if I'm reading this thing from left to right, it's going from a y value over here to a y value over here. Right, so I call this y0 and y1 if I want. But when it gets to this location, it's not as simple as saying it's a constant value. It's just that really going from one part of the graph to the other part of the graph. Right, so that's really all there is to it. It's just a matter of identifying what the relationship is. You know, it's kind of overkill in terms of the explanation, but maybe that helps. I don't know. That's the plan anyway. So if you did it from the other perspective, it's fine. It's just a whole lot of things would reverse, right? So if I'm going from y equals this to y equals that, it's pretty clear that those should be x expressions. But if I'm going from x equals this to x equals that, then it's pretty clear that it should be y expressions, right? So you know, it's part of the fun, right? So, and in this case, if I want to label it up, I could say y. I'll call this one the y0, y1, just so it corresponds with my diagram, right? But one part of it is the x squared minus 1. That's the low bound or the bottom half, and 1 minus x squared is the top half. And then once you figure out what the restrictions are on that function, that gives you the balance for the other integral. All right. So, like I said, it's a little overkill in terms of the explanation. I always kind of struggle with reading my audience on whether or not they understand what the heck I'm talking about when it comes to this stuff, because it's kind of hard to tell even when you're in the classroom environment, that you sometimes have students that, you know, that they'll smile and nod, and it's kind of hard to tell if they actually understand what I'm saying. But yeah, I figured I'd rather overdo it with the explanation and kind of talk your ears off and probably give you more than you need than than to cut it short and kind of put you in a spot where, you know, you're not getting what you need out of this. All right, so that's the idea anyway. So let me move on. Get another example there. Actually, you know what? This other example is pretty pretty simple by comparison. So let me put a star on this one so you can try it. All right. I didn't realize that there was a what you call it, a little fraction jammy there that would have helped us out a little bit. 8/7 as opposed to writing the 1.143, but it's there, so why not, right? So let's well, let me stop this recording and start a new one.